Welcome to video lecture B6. This one is on bases for the null space and column space of a matrix. I'll be your tutor, Tom Roby. Here are the outline and objectives. So all we're planning to do is to compute bases for the null space and the column space of a matrix A. And let's start with an example. So we know that the column space, we have two ways of thinking about the column space. One is it's the set of images of the matrix viewed as a linear transformation, and the other is just as being the span of its columns. So let's just take a quick look at B here, right? So B is much easier to understand. It's the row-reduced echelon form of A. And if we're going to have a basis, well, what do we need? Well, every linear combination of these four vectors is going to have 0 in the bottom component, right? And the only way you can get things in this component is to have this 0, 0, 1. So we've got to have that vector. And similarly, if you have this vector and the fourth vector, then you'll clearly be able to generate anything that's in the span of all four of these vectors, because you can get 1, negative 2 as the linear combination, one of these minus two of those. Okay? So this third column is really extraneous as far as the column space of B goes. Now I'm talking about the column space of B, not the column space of A. But let me just formalize what I said. I said that if I take the negative of this vector plus 2 times this vector, and I add it to this vector, I get 0, right? Another way of saying that is if I rewrite this equation, that I can write B3 as B1 minus B2. Okay? Now this is equivalent to saying that negative 1, 2, 1, 0, this length 4 vector, is actually a solution to Bx equals 0, right? Because multiplying this matrix B by this column is just taking the linear combination of the columns of B given by this. So it's just negative 1 times this, plus 2 times this, plus 1 times this, plus 0 times that equals 0, right? So this is a solution to that, and you can just double check it if you like, right? But here's the key. If this vector is a homogeneous solution to Bx equals 0, it's also a homogeneous solution to Ax equals 0, right? Because that's how row reduction works, to preserve the solution sets. What does that mean? Well, that means then that if I look at the linear combination negative A1 plus 2A2 plus A3, that should also be 0, right? Because this is still in the null space. It's a solution to this, so it's a solution to this. So I can put it here. And let's just double check. If I take negative 1 times this plus 2 times this, then I get negative 1 plus negative 1 plus 2 times 2 is 4, right? So that's positive 3 minus 3 equals 0. Good. Here I've got minus 2 plus 5 times 2 is 10 minus 8 equals 0, and so on. So you can check that in every row that's true. So the third vector here, A3, is also equal to A2 minus 2A1. Okay? So that's really the key thing, right? That the fact that B3 was equal to B1 minus 2B2, right? Those column vectors implied that the same thing was true. The same linear dependence relation was true for the columns of A. So this is really a key fact, right? That row operations preserve linear dependence relations. So a set of columns of A is going to be linearly dependent or independent if and only if the corresponding columns of B are, right? So armed with this, we're able to come up with the following proposition. We basically know how to figure out what the column space of A is, right? What we need to do is say, well, the pivot columns of A, the pivot columns of B are going to be the things that are linearly independent, right? Because it's clear that if you have something that's not a pivot one, then you can write as a linear combination of the previous ones, just like we did here. And it's only at the pivots where you're adding something new, which has no zeros above it and nothing to the left of it. So the pivot columns of B clearly form a basis for the column space of B. But because linear dependence and independence is preserved, that means that the pivot columns of the matrix A form a basis of the column space of A. Now, this is the dangerous bend sign, which means there's something to be careful about. We need to row reduce A in order to figure out what the pivots are. We may not have to put it in row reduced echelon form. Of course, if you have a computer, then you might as well. But you need to row reduce it far enough to figure out which ones are the pivot columns and which ones are the non-pivot columns. And then you're going to take the pivot columns of your original matrix. Okay? So the point here is that a basis for the column space of A is going to be A1, A2, and A4, right? The first, second, and fourth column. So it's the same columns here, but it's the columns from A. Because, I mean, just as a quick example, if you look at the column space of A, if you take linear combinations, you'll certainly get things that have a non-zero fourth component, a non-zero x4, right? But over here, you only get things that have a 0 x4. So it's certainly not true that the column space of B and A are the same, okay? So doing row operations changes the column space, but it doesn't change which vectors are a basis for the column space. So it's a really interesting idea, and it's very useful, and there will usually be problems on final exams that ask you to figure out what a basis is for the column space, and you have to not be trapped into thinking that you can use the columns of B. Right? How about a basis for the null space? Well, it turns out we already know how to do this. We've been doing this for a long time. So let's take the same example now, where we've got this matrix A, and its row reduced echelon form is B, and you say, okay, well, how do I figure out a basis for the null space? Well, I'm just trying to solve the homogeneous system. Ax equals 0, which is the same as solving the homogeneous system Bx equals 0. So I look at this form, I say, okay, x1 equals negative x3, x2 equals 2x3 from the second equation, and x4 equals 0 from the third equation. The fourth line doesn't tell us anything. And so then you say x1, x2, x3, x4 equals, according to these equations, negative x3, 2x3, x3, 0. You factor out the x3 as a free variable, which becomes a parameter, and you see basically that the solution set to either bx equals 0 or ax equals 0 is just all multiples of this vector. Right? So we already saw that this vector was in the null space, right, when we were looking on the last slide. But now we see this is actually a basis for the null space of A equals the null space of B. So this procedure we've been doing all along will always generate a list of vectors that's linearly independent. So that's the key thing. All right, back in the column space, the point is that we start with it being the span of all four of these vectors, and then we just gradually throw vectors out that are linearly dependent. And we do that until we have vectors that are only linearly independent, and we're good to go. For the null space, it's the ordinary procedure. And so once again, let me emphasize this dangerous curve. The null space of A and the null space of B are the same. So when I convert A to B, I'm not actually changing which vectors get sent to 0. Okay? But when I change A to B, I am changing where things go when I think of them as linear transformations. The column spaces are not equal. So I think that's it for this video lecture. Thank you for your kind attention.